Okay, so in this problem we're asked to find the volume of the solid generated by revolving the region bounded by y is equal to 4 square roots of x and the lines 4 square roots of 3 and x equals 0. About 4 different things here. We've got the x-axis, the y-axis, the line y is equal to 4 square roots of 3, and the line x is equal to 3. So I'm going to set up and explain all these integrals. I'm not going to actually solve any of them out, but I will set them all up. Okay, so for the first one, we've got this region here, and we're revolving this around the x-axis, which is down here. Okay, so our axis of rotation will be this axis. So imagine this region here going around the x-axis. Notice that if you take maybe like a little bar here, draw a bar. Imagine this bar is going around the x-axis. There'll be a gap in it, a hole in it. So we're going to use what we call the washer method on this, which means we need a big radius and a little radius. Okay, so for this one, we're going to have the volume is equal to pi from whatever our limits are, a to b, of your big radius squared minus your little radius squared dx. We're going to be integrating with respect to x because we're rotating around the x-axis. Okay, so our limits of integration are going to be from 0 to 3, here to here. Okay, so we're going to integrate this bar over this region, starting here and going to where they intersect here. So from 0 to 3, so it'll be pi from 0 to 3. Okay, and then our big radius, we need to think about this washer. Which one's bigger? Is it this inner part with the hole, or is it this outer part? And it is definitely the outer part. That's the bigger one that's going around wider. It's coming out and going down through the paper like this. So it's definitely the bigger part. So that's going to be our big R. So our big R is going to be 4 square roots of 3 squared. And our little r will be this inner part as it goes around the x-axis, which will be this 4 square roots of x. So 4 square roots of x squared. And then we'll integrate that. I'm not going to finish the problem, but that is the setup of the problem for part A. Okay. So for part B, do it here. Okay, we've got the same problem except we're rotating around the y-axis. Okay, so we're going to be rotating this direction now. Okay, so since we're rotating around here and the region is actually touching the y-axis, which is what we're rotating around, there's not going to be a hole like there was with the x-axis. With the x-axis, there was this gap in the middle, which forced us to use the washer method. But here, there's no distance between the axis of rotation and the region here. So we're going to get to use the disk method, which means we only need to use 1r, which will be the region itself, and from A to B, and it will be r of y because we are a function of y because we are rotating around the y-axis, so it'll be dy. So if you look at the distance between the axis of rotation and the edge of this region here, it's this function. But this function is an x function. We need to change it to a y function. That's pretty easy to do. We just write it down here, solve it real quick. So I'd move the 4 over, and I would square the x, which means I would need to square this other side. I know I'm doing that kind of fast, but that would be your y function, which is y squared over 16. So our volume there would be, I'll do the limits in a second, it would be y squared over 16 dy. Our limits will have to be y limits, so from here, which is 0, to our upper limit of the region here, which is that number right there, 4 square roots of 3, because we're now rotating around the y-axis, we need y limits. So 4 square roots of 3. Okay, and that will be our setup for rotating around the y-axis. Okay, now let's do part C. C says we want to rotate around the line 4 square roots of 3. So now we're rotating around this line here. Okay, so it's still going to be this bar here, the same one that I drew for letter A, except we're not rotating around the x-axis like we were. We're rotating around this line here. Okay, so there's no gap between the axis of rotation and the area there. So we can still use the disk method instead of the washer method like we did on A. So it's again going to be pi from A to B with just one r. And since the line 4 square roots of 3 is horizontal just like the x-axis, then this is going to be an x function. So it'll be dx. Okay, so we just need to figure out what's the distance, what's the length of that bar there. Okay, and the length of that bar there is the distance between this upper function and this lower function. How far is this one bar here in general? Okay, so that's going to be, we'll do our limits in a second, that's going to be 4 square roots of 3 minus 4 square roots of x. It's the distance there. You do distance by subtracting the top one minus the bottom one. Okay, so that will be 4 square roots of 3 minus 4 square roots of x. That is the distance of this one bar, which we're integrating over this area as we're rotating here. Okay, and it's squared, so that'll be dx. Okay, so it's a little different than it was in part A when it was x-axis and it had the hole there. The hole forced us to do what we did on letter A, which was do big R squared minus little r squared. This one is just 1r, but the distance of this line is found by subtracting the two functions there, the upper function and the lower function, and then squaring. Okay, all right, so I'll let you guys figure out that integral. Let's go on to D. Okay, the line x equals 3. That's this one over here. This line x equals 3. So we're rotating now around that. Okay, which is the same direction as the y-axis, so it's going to be a dy integration. So we've got v is equal to pi a to b. Now let's see if this is washer or disk. Let's look at the what's going to happen as we're rotating this region around this. Notice there's going to be a gap here. As we're rotating this region around that line, there's this big hole in the middle, so we're going to have to use the washer method. This is going to be big R sub y, or r of y squared minus little r of y squared dy. Okay, we need to figure out our two r's. So let's go with our bigger one. Which one's further away from x equals 3? Is it the function here, or is it all the way to the edge of this region here, which is actually x equals 0? Well, it's definitely all the way over to x equals 0. So our big R sub y, write it over here, is equal to 3 minus 0, which of course is 3. Okay. Our little r sub y, which is the distance between the axis of rotation here and this function, okay, is definitely that distance. Now remember, we're in terms of y, so we can't use 4 square roots of x, but we can use what we already solved for earlier, which was x is equal to y squared over 16. That's the same function. We just solved one for x. Okay, so our little r of y is equal to 3 minus this. That's a distance. This minus whatever this is will give us that distance. So 3 minus y squared over 16. Okay, so our final setup here is from pi, do our limits in a second, 3 squared minus 3 minus y squared over 16 squared dy. Our limits are going to be y limits because we're going in that same direction as the y-axis. So that'll be like that was on letter B. So it'll be from 0 to 4 square roots of 3. And then solve that integral, get your answer.